Hello everybody. It's 4:05, which is 4 sharp Spanish time. Uh, it's my great pleasure today to introduce John McCalpin. John is a research scientist in the High Performance Computing Group of Texas Advanced Computing Center, TAC, as you can see on the slides and on his T-shirt. He joined TAC in 2009 after a 12-year career in performance analysis and system architecture in the computer industry. 3 years at SGI, 6 years at IBM, 3 years at AMD. Prior to his industrial career, John was an oceanographer. Did I pronounce this?
Oceanographer?
Yes, that's the one. I don't get that word too frequently in my English. PhD from Florida State, 6 years as an assistant professor at the University of Delaware, where he was engaged in research and teaching on numerical simulation of the large-scale circulation of the oceans. John, or Dr. Bandwidth, is the best known for his work on stream benchmark, but he did much more than that. Today he will talk about the history of supercomputing systems with a focus on the balance between computation and memory access, and on the interaction of technology, architecture, and market forces in driving the evolution of these systems. Which is nice.
Sounds good.
Sounds great.
Yeah.
Sounds great. So it's this is a hybrid talk. So we have people in the room, we have people at Zoom. For the people at Zoom, if you have any questions or comments, be free to chat. After the talk, we will select a couple of them that we will address in the QA session. For the people in the room, we will have some coffee and treats after the session. And this is a great opportunity to have an informal discussion with our guests. And also for people who are in Barcelona these days, John will be with us until 21st of October. So if you would like to meet him, chat, talk, this is his email. And with that, I'm leaving you the floor.
Yes.
Thank you for being here today.
Thank you for inviting me. Okay, let's see. There. Hello, it's a pleasure to be here. The talk that I'm going to give today, this is, I think, the third public version. This was developed originally as an invited talk for the Supercomputing 2016 conference. I updated it in December of 21 for a group of my colleagues at Friedrich Alexander University in Erlangen, who I have great fun talking to, and I'm actually very happy that I got the incentive to review this again, because many very interesting things have happened in the markets and in the technology since 3 years ago. So I'm going to talk about technology changes first through the lens or with the tool of the top 500 list of supercomputing systems. I'll talk a little bit about what that is. It's may or may not be a good measure of anything, but it does provide us an opportunity to look at different things and talk about them. Then I'll talk about the technology trends that are leading to changes in the system balances and changes in the way we need to think about computing. So part one. The top 500 list was developed in 1993 by Jack Dennard at the University of Tennessee to pull together the list of the 500 fastest computers on the high-performance LINPACK benchmark, which was solving a dense system of linear equations using Fortran code that Jack's group had developed. Of course, it only includes systems that have reported results. So if someone decides not to list their machine, it doesn't show up. There's a lot of strange things we might call games that vendors who want to use this list for marketing will exploit. So, for example, a benchmark only needs to be run on one instance of any configuration. And it's assumed that if you sold 20 of those, all of them would get the same performance, and you could just. I got a nice bonus one year when I worked for IBM for coming up with a formula that would determine which configurations would probably go fast enough to make it onto the next list so that we could limit our testing to one of each of those. The system doesn't have to be used for HPC. In the early days, the fact that you're doing well on high performance LINPACK means that you have high performance 64-bit floating point, which was pretty much only implemented in systems that were intended for high performance computing. That's no longer the case. So a lot of commercial and database clusters, you'll find telecoms, cloud services. The results are submitted by the owners, in some sense, the people who own and manage the machine. And they get to choose how they want to submit their results. If you have a really big machine, you might submit it twice to get two smaller entries. Most people go for one big one, but there's funny things that happen if you try to look at, and something I try to avoid doing, which is looking at the count of systems on the list. IBM has 210, HPE has 180, whatever. Those numbers are easy to skew by the way you've chosen to aggregate and disaggregate your system. So, but you'll see that in marketing. Many systems are now heterogeneous, and while the software for a homogeneous cluster is readily available to run the benchmark, it's much less available for heterogeneous clusters. Sometimes they're reported as separate, even if they are physically in the same room and could be run together. Now, this is the fun part. Jack Dungera maintains this at the university at top500.org is where it shows up now. You can download the data in XML files, but that doesn't include any system configuration data. So you have to do Excel, and it's horrible. It's horrible because there are 15 different combinations, 15 different database formats used over the 63 lists. There are illegal characters in most character sets, and horrible, horrible ways. So my original approach, I spent hundreds of hours just sort of fixing this manually, and a lot of what I have to do is get on Google and look up what the parameters of the system are, because he'll give you some of the parameters. He'll tell you how many cores it has, but he won't tell you how many nodes it has. And the number of cores is often wrong. In fact, there are many hundreds, if not thousands, of errors in the raw database. So a lot of reverse engineering is required. Today's results come from this more systematic reanalysis. Still has a little bit of manual intervention, but I'm trying to put this in a more reproducible, auditable approach. Mostly because once I make a decision about what a system is, I don't want to ever have to go back and think about that system again. Okay, so the big picture here that I'm going to start with is for each list, I'm dividing the systems according to what I consider to be their architecture. The top 500 list also has an architecture category, but this does not mean the same thing as that. Because I came from the computer industry before my current position, I'm much more interested in sort of how these machines get paid for. So starting, okay, RMAX is the gigaflops on LinPack. I sum it up over all of the systems. So in the beginning, in the early lists, in the early 1990s, oh, that's funny. Um, the the decimal indicator has changed automatically because I'm in Iberia. Okay. So originally the machines were primarily vector machines. They dominated since the early 1980s, and by the early 90s were still this dominant force. Then through the 90s, the majority of the performance on the list was from what I'm calling RISC as a shorthand, and it means CPUs that are not x86. Um, in the original presentation, I break this down into the 7 or 8 different vendors: DEC Alpha, HP, PA, RISC, IBM Power, but I'm not going to talk about that today. Then following that, there's a very large x86 starting in sort of 2004, 2005 with the AMD Opterons and then Intel's follow-ons. One category that's very different than the way the top 500 list does it is I have a category called MPP, massively parallel processor, or specialized. And what I mean by this is that the the money to pay for the development of the system comes only from over $1 million supercomputing sales. It can't leverage anything smaller than that because nobody bought them in smaller um, configurations. And I'll talk more about all of these. And then starting in 2008, we have this new category of accelerated systems. So this was the state of, so I gave the presentation in 2016. You can mentally mask that off. And between 2016 and 2021, accelerated grew and changed, and there were some changes, but it was also not completely obvious what the trends were going to be. Um, there we go. Now it's obvious. Immediately after my previous review of the data, the accelerated systems took a huge leap. The MPP systems didn't get smaller. The same ones are still installed, but they didn't buy more of them. The x86 dropped dramatically, and there's a new risk component that I'll mention in a minute. So we're now up to about 76% of the RMAX of the top 500 list comes from accelerated systems. Not all of that is from the accelerators. Some of it is from the host processors, but the majority of it, certainly in excess of 90%, is probably from the accelerated systems. That I think that has an important message for users, because as recently as December of 21, when I did this, it wasn't completely clear that I needed to switch to accelerated programming models. I didn't want to. I still don't like it a whole lot, but that's uh, I'd say the new NVIDIA Grace Hopper chips are really nice. They're really easy to use, and doing accelerated computing on that system is very pleasant. So now it's pretty clear, although there'll be some caveats here. A new number one system often brings kind of noticeable changes in the list. Here in the late 90s, ASCII Red was the first x86. The Earth Simulator was a vector machine that made a big boost. Blue Gene L was big MPPs. Roadrunner was actually the first accelerated system. How many people here remember Roadrunner? Anybody? Yes, a couple of us old folks. Roadrunner is AMD Opteron processors with IBM Cell processors as accelerators. And it's a horrible mess. It's a horrible mess because they have different cache line sizes, different endianness. Um, I was working at AMD at the time as the technology lead for our tightly coupled accelerator program. And I am really glad that nobody told me that I was responsible for that. um, because it's not the right way to do it. But it was the first system to break 1 petaflop, I guess. Um, the K computer, big all RISC um, system, Blue Gene Q in the MPP. Tianhe 2 was the first really big giant accelerated system. Taihu Lite I'm classifying as an MPP for largely because the you can imagine buying one CPU with one GPU card and doing offload programming on that. It's hard to imagine buying one of these Sunway processors that has 4 quadrants, each of which has one kind of medium powered general purpose core and 64 very specialized offload cores. It's just not the kind of thing that is going to have a significant market behind it. Summit, giant accelerated machine. Um, Fugaku, right, the A64FX ARM processors, and then the Frontier system. So looking at how much of the list's RMAX comes from accelerated systems by accelerator provider, I think it's very interesting because initially IBM Cell in just before 2010, NVIDIA GPUs have been there all along. Intel Xeon Phi had a blip. We had one of the large systems with that configuration. The Matrix 2000 accelerator in Tianhe 2 was a pretty nice piece, and that's where I ended the previous version of the report. And so, poof, everything completely changes. We have extremely large AMD GPU contribution now with the Frontier system, and actually a fairly sizable Intel GPU. If I could remember the name of the system at Argonne, I would tell you what it was, but it's it's that one. It's their system. So there's been a lot of changes. The one that I kind of worry about the most is what sort of thread concurrency do you need to use a top 10 class machine over time? Well, the old vector machines, you could four threads. That's what you needed to run the machine. Now, uh, Frontier, for example, up, it says 8 million or 500 million. There are 8 million graphics clusters, which each require about 64 threads of execution. So you're 500 million threads of execution versus 4 in, I guess it's been about 30 years, but that's still a lot of orders of magnitude. And it doesn't make a lot of sense to me to think that you can take the programming models that were still very similar to what we were using in the 1990s and scale it up by eight, 7 or 8 orders of magnitude in thread count. An interesting behavior is that the list is becoming increasingly top-heavy. Part of this is politics. Governments want bragging rights to owning the biggest machines. They're also getting a lot more expensive. So what we see here is the bottom line shows how much of the list belongs to the number, how much of the aggregate performance of the list belongs to the number one machine. That first changed in 2002-3 with the Earth simulator, and then kind of settled back down, and now it definitely seems to be on the upward trend. So people are buying these absolutely massive systems, and if you include the full top 10, It's a significantly bigger shift that we've gone from 24% of the performance to over 50% of the performance is in the top 10 machines. And that's an odd that's an odd thing to happen from a sort of a market perspective, because what typically happens in a market is that something cheaper and not quite as good comes out. And so there was actually probably from the in the middle, the first decade of the 2000s, I think there was a really big move toward people buying their own clusters. A professor would have a cluster of 8 Dell servers in his closet. Um, and it seems like the money for that sort of investment has mostly gone away and has gone into these gigantic uh, sort of billion-dollar class systems. So now I want to change gears and talk a little bit about the technology trends that are related to what's happened in the market and perhaps more interesting for looking forward. Performance can be viewed sort of as uh, a vector, a set of independent vectors, orthogonal vectors, and arithmetic performance, memory bandwidth for streaming transfers, memory latency for non-overlappable, non-prefetchable transfers. There are similar benchmarks for interconnect bandwidth and interconnect latency. I won't really talk about those latter two very much today. And the system balances that I talk about are the ratios of those components. In particular, I like to talk about the cost of a floating point operation in execution time versus the cost of the memory references that feed into that floating point computation. So peak flops are still increasing at ridiculous rates of 50% a year. Memory bandwidth is increasing much more slowly. Latency, which you would like to go down, is actually going up systematically. Interconnect bandwidth is going up modestly, and interconnect latency is coming down modestly. So these ratios over time suggest that we're going to be getting increasingly imbalanced and have increasing difficulty using the machines effectively, efficiently. So this is my ratio. This is floating point operations per second, the peak floating point operations per second rate, divided by the sustainable megawords per second of memory bandwidth. And so it has words of units of flops per word. In the old days, you needed to, well, if you have a value in the 10 range, for example, you could do 10 floating point operations in the time required to load a word from memory. And this is for streaming, prefetchable, contiguous, the easy case. And it didn't take a whole lot of cache to give you some reuse so that you didn't slow down by 10x coming from memory. You only slowed down by 2x or 3x, something like that. And for values in the 10 or 20 or even 30 range, the machines were really quite easy to use. You didn't have to spend your entire life figuring out how to cache block and get reuse. But once we shifted to multi-cores in the 2005 sort of era, this started getting out of control, and there's some other factors. To get up to where many systems are now well over 100 floating point operations per word in terms of cost. So that if you're running a streaming workload like the stream benchmark, you're therefore going to be running at under 1% of the peak floating point rate. Now, I added some new machines from the previous presentation. It looks like things are going in a good direction. And for those data points, they sort of are, but I wanted to explain a little bit more about why I wouldn't read too much into that trend-wise. The Intel Ice Lake Xeon block up there is pretty much on the curve. That was for a 40-core chip in my lab. Right below it is an AMD 7763. I think that's of the Milan. That AMD typically has slightly, well, let's put it in. AMD has half of the peak bandwidth per cycle of Intel. And so that gives you a factor of 2 improvement in this balance parameter, which sort of leads to what I call McCalpin's law, which that any ratio can be fixed in the wrong direction. I'm not really complaining. I'm not saying they're doing it wrong. I actually like those processors a lot. But it doesn't mean that they've figured something out or doing something different. The next one, Intel Sapphire Rapids with DDR5. There are a whole bunch of them across the street. How many thousand? 6,400 nodes or something like that. So 13,000 of those processors. It's got pretty good bandwidth because they didn't increase the core count too much, and they did increase the DRAM bandwidth with DDR5. Straight below it is the Intel Sapphire Rapids with HBM, which looks like a huge improvement, and it's a fine improvement. It's a very easy to use processor. It also doesn't have a follow-on in the next generation. Uses HBM memory, and they're not going to do that in the next one, but they might do it in the one after that, and we don't know. Becomes very difficult to predict. And the last one is the NVIDIA Grace, which has also a lower floating point operations per core per cycle than Intel, but has an interesting approach to the memory system that gives it a substantial memory bandwidth increase. That's why I like those processors. But none of this changes the underlying technology trend that it remains cheaper to add flops than to add any other kind of performance. So that bottom, that curve is now the lightly shaded curve at the bottom. That's the cost of fully prefetchable streaming accesses. And the next curve, which I had to add 2 more orders of magnitude on the scale, is what happens if you have a cache miss in all levels of the cache that you can't overlap with anything. And now we're looking at 10,000 floating point operations cost for 1 memory reference, which when it was even 100, it was okay. But when these numbers get so high, you don't have to do it very often for it to start being very painful. And this is not even the worst case. This is looking at 1 core stalling on a memory latency. With a hybrid programming model, you could have the primary thread stuck on a memory latency, and none of the worker threads can progress until the primary thread resolves that latency and makes a flow control decision or whatever. Also, it's important to note here that we did see these big differences in the balance for floating point, for streaming data accesses. But when you switch to latency, those differences mostly go away, and everybody's back on the sort of the technology curve. So why are the flops increasing so fast? Well, this peak value is the product of usually 3 terms, and they get driven at different rates. I like this picture. It hasn't been updated, but it gives me a nice graphical view over time for Intel processors. The Pentium 4 had 2 floating point operations per cycle at about 3 gigahertz. Then they moved to the Core 2, and it doubled it to 4 floating point operations per cycle, and then they added more cores dropped the frequency a little bit. Nehalem-Westmere stayed at 4 per cycle, started adding more cores, bringing the frequency up, and so on. You add more cores, you add more floating point operations per cycle, you add more cores, frequency is the same or lower. And that's sort of the situation that they're at now, except that instead of having 24 cores, Sapphire Rapids is 56. Granite Rapids will be more. And so it's the multiplication of these parameters that leads to the super high unattainable flops rate. Bandwidth is increasing more slowly, partly for simple technological reasons. A lot of the emphasis in the industry is on increasing capacity, not increasing bandwidth. It's a different set of problems. Usually in HPC, we're not limited by capacity. If we have a job that is parallelizable over multiple nodes, you just keep on adding nodes till you have enough memory to run the job. Even if your scaling is not great, at least you can do it. So that gives you much less need for a giant monolithic multi-terabyte node, although sometimes those are nice to have too. The shared bus architecture of multiple DIMMs per channel, it's ridiculous. It's very hard. Where the point-to-point links of InfiniBand have been running at 25 gigahertz for a while, we're now getting up to 5 on DRAM with DDR5. So there's a big spread there. Underneath this is a very important point about DRAM cell technology, and that is it's almost unchanged. The amount of time required for you to what's the right word? Activate a row, move it into the sense amps, read the data, push it back to the row, and that was 60 nanoseconds 20 years ago, and it's 48 nanoseconds now. So, 25, 30% in 20 years is not consistent with the other sorts of improvements that we're talking about here, orders and orders of magnitude. So the only way they've been able to get increases is to increase the transfer sizes, the burst rate, the burst length. DDR5 had to go and cut the channel width in half because they needed to double the burst rate again to a burst length to a 64. They didn't want to go to 128 byte transfer because so many systems still use 64 byte cache lines, and the only way to do that is to split your DIMM in half to have two 32-bit channels. And of course, pins cost money. So what about latency? One big problem in latency is that we have more levels in the cache hierarchy. Lookups are typically serialized to save power. Even if they're not serialized, looking up an address in a larger data structure will always take more time than looking it up in a smaller data structure. One thing that I think is underappreciated is that modern systems have a ridiculous number of asynchronous clock domain crossings. And this was something that we didn't have to deal with even 15 years ago. We weren't really doing this in the server space. We're just starting to look at it. That typically you would just run everything at the right frequency. The core and the non-core part of the chip out to the memory controller would be running at a fixed ratio that was easy to deal with. And so the only asynchronous boundary would be to the DRAM typically. And some designs even fiddled with the DRAM frequency to make that work better. But now we've got cores that run at variable frequency. The uncore mesh runs at a variable frequency. The chip-to-chip connection works at another frequency, the DRAMs. And in order to, depending on which vendor you are, in order to have the appearance of a shared cache, there are the addresses have to be distributed around all of the different L3 slices on the cache, which means that you're doing a lot more of these hops than across the network mesh than you used to do. And the reason that you have to do the distributed cache is because you're trying to maintain coherency, and you can't snoop more than one core's worth of accesses out of a cache. In fact, uh, there are typically some compromises made because you don't like on a Skylake, I think was the last time I looked at it. The L2 cache on a Skylake, the tags are still single ported, and it's possible for that to slow things down because of collisions between requests from the L1 and requests from the prefetcher. So we want to minimize coherence as much as possible, and that means much more sophisticated systems of directories and multi-level lookups. And frequencies are going down. I was really surprised when I ran on the Sapphire Rapids with HBM. This was, I can't remember if it was on the production levels or not, but when I was running, say, the stream benchmark, which is not usually considered a memory or a power hungry workload, each core is graduating about one instruction every 16 cycles. So it's mostly just sitting and waiting. And in order to keep the cores at their desired frequency, the uncore mesh dropped from 2.4 gigahertz to 1.6, which actually ended up making it slower because they didn't choose to save power in the right place. They should have kept the uncore clock up high and dropped the core frequencies, but they didn't know what I was trying to do. It's just an indication of the increasing difficulties of managing power in these systems. A different implication that it's my, I guess, main point here is latency, bandwidth, and concurrency. This Little's law, the great computer architect Burton Smith taught me about this, going all the way back to the 1990s. Little's law describes the relationship between latency, bandwidth, and concurrency in a super easy equation. And in a whole lot of cases, if you know two of these values, you can compute the third one. But sort of the trends, if the latency is flat and the bandwidth goes up, then you have to increase the amount of concurrency, the number of cache line transactions that are pending, in order to increase the used bandwidth on the interface. If the latency is going up, then it has to increase even faster. So I have to go all the way back to 2005 to find a concurrency example that was small enough that would actually be visible on a slide. So this was an Opteron in 2005 with 60 nanoseconds main memory latency, 6.4 gigabytes per second. So it took 10 nanoseconds to transfer a cache line. In order to tolerate the 60 nanosecond latency, you had to have 6 10 nanosecond transactions pending at all times. And that was nice because you could do that with one core on that system, and it was very, very efficient. And maintaining a buffer with 6 outstanding misses was not expensive in design, in area or design time or power. The numbers are not the same anymore. Notice that this is a logarithmic scale. This is the number of 64-byte transfers that need to be outstanding based on the minimum latency in order to tolerate the latency for a socket. And the blues are for CPUs. It went from a handful. I think there's the 6 number. Well, it's number near 6 in 2005, a little lower. now we're headed up to hundreds of cache lines outstanding. And the two blues that are above that are the high bandwidth CPUs that, they look good, but you now have to have another factor of 5 or 6 more concurrency. And then the top is for NVIDIA. Well, there's one Xeon Phi number in there, but mostly that's NVIDIA GPUs over the same sort of time period. And both of those numbers, the amount of concurrency that you need is going up by about 25% a year, which is very difficult to manage using traditional programming models and traditional architectures. Why is that a problem? So the architectures are built using a flat memory model. If you look at the architectural documents, the location of the data is unknown. You do a load instruction and eventually it will be loaded. And the hope is that caches and prefetchers will enable you to be good enough. That it's not so, that's kind of optimistic. Implementations support very limited numbers of data cache misses. Sapphire Rapids can only support 16 L1 data cache misses per core. But that chip needs, 400, 500 outstanding cache misses. So you have to use an awful lot of cores just to get the DRAM bandwidth. For HBM, if you wanted to get full bandwidth out of the HBM, you would need to support 64 cache lines outstanding for every core. The hardware only supports 48, and it doesn't actually give you 48 when you want it. And the reason for that is that beyond the 16 L1 misses, if you want more outstanding misses than that, they have to be hardware prefetches. Hardware prefetches can't be controlled. They happen or don't happen. You can, in some cases, you can turn them off. In other cases, you don't have permissions to turn them off. In other cases, you try to turn them off, but the hardware says no, which is kind of fun. On the Sapphire Rapids with HBM, if you turn off the prefetchers, they keep on prefetching. And I don't blame them really, because there's so much bandwidth. You can only use about a third of the HBM bandwidth on that system, maybe half if you're very talented. So you're in a very flat part of the latency curve. And so doing prefetches is not really going to cause any harm. Another problem with concurrency is that you need to run a lot of cores just to generate the cache misses, even if you don't need them to do the computing. So like on the stream benchmark, for example, I'm graduating one instruction every 16 cycles. I can do the whole chip's worth of computation on one core running at about half the nominal frequency. But there's no way to do that. I have to use, in most of the processors, at least 16 cores, and the newer processors, 32 or more cores, just to generate enough concurrency. And that costs a great deal of energy. That's measurable and easily tested. Also, in order to handle this concurrency, the way it's currently being done is you need huge buffers and complex memory controllers. And every cycle, they're reviewing the outstanding, the pending DRAM reads and deciding whether or not they want to close a page and open a page. That is that's expensive in design time and validation. It's expensive in silicon area. It's expensive in power. And even so, they don't do that great a job. It's amazing to me how well they do. But you lose on say an Intel processor with DDR5 memory. Well, DDR4 is the numbers I know better. You're typically 78% utilization is about the max you can get if there are any stores in the workload. And so that's 20% of your bandwidth that you're not getting. Sort of seldom appreciated side effect of this is if you use more cores to make the memory references, each of those cores is going to be operating on a different piece of the address space. And so it's going to be generating another set of access streams that go to the memory controller and need to be mapped onto the DRAM banks. But we don't have any more DRAM banks than we had before, and we have twice as many cores. This is an older example, but absolutely everything still applies. If you have we had one case where with similar processors, 12-core Xeon E5 V3s, when you run the stream benchmark, several of the kernels have two streams, a read stream and a write stream, or two read streams. And running on 12 cores, that gives you 24 streams, which means 24 banks, but we only had 16 banks. So what happens is the hardware has to close the banks and reopen them and close them and reopen and close them. And that cost about 15% net bandwidth reduction on that system. And if we switched from a 16-bank DRAM to a 32-bank DRAM, we recovered that performance. Now, that's for 12 cores. Now we're looking at 60, 70, 120 cores. And if you use hyperthreading, you've just doubled all of this over again. And so the bandwidth doesn't usually drop very much. 5% is a typical number. But the power required continues going up, and you're getting less performance out of it. So the way I usually describe the problem is the architecture does not give the user a way to specify what you want the hardware to do. And so it has to guess. And it guesses by predicting when to open and close pages. All of that information, or not all of that information, but a huge amount of information about the locality, about future accesses, is available at compilation time. It's available by reviewing the source code and looking at loops. But that gets thrown away, and the compiler turns it into a serial instruction stream. And then the hardware has to begin discovering parallelism and predicting the future out of that. And it happens at the L1 cache level, it happens again at the L2 cache level, happens again at the memory controller level, and every time you're losing a little bit of, you're making imperfect predictions that are then multiplied together to give you kind of boring performance. So that's really what I wanted to talk about today. The one message about the top 500 analysis is that really the basic characteristics of our high-end supercomputers have changed repeatedly over the past decades. And we often are so focused in the now that we don't think that, oh, this is going to happen again. You know, in another 6 years, there's a very good chance that it will look nothing at all like what we have, and that we need to be sort of aware of this. The technology trends are definitely improving the cost, reducing the cost of computation. So we have increasing imbalance, even in the very best case where we can predict everything and prefetch everything. That's likely to continue. In fact, it's pretty close to guaranteed to continue. So in order for our application performance to track the increases in bandwidth, we need rapidly increasing concurrency. So our same application, rapidly increasing concurrency. That's not an impossible thing to do. If we want to increase faster than the 20% we get on memory bandwidth, closer to the 50% we get on flops, we need to increase the compute intensity. And that's a significantly harder thing to do, because in most cases in which you're looking at the study of algorithms and locality and reuse in the algorithm, when you specify the algorithm, you're kind of done. You know how much reuse there's going to be. And if the next computer requires twice as much, the math doesn't support it. Now, if you make the caches larger, you can get some benefit. If you could improve cache reuse by more direct control, or finally you're left with new algorithms, which is typically a very expensive multi-year sort of redevelopment effort. So my question that I end up with is, why is it that given these technology trends, we are not spending more time and money trying to design architectures that allow us to control the most expensive things in the system, the data motion, including synchronization, that are increasingly dominating the cost of computing. I think it's an interesting conundrum that software portability and reuse is considered to completely reject any possibility of changing the architecture in a way that will be less butting heads with physics. Yeah, we can. There are approaches that can help us use the hardware much more efficiently in terms of physics, but there seems to be little work going on in trying to make those things happen. Zoom quit unexpectedly, so I hope anybody got in a question, but that was indeed my last slide. That's good timing. The magic buttons.
I believe that this was the bandwidth issue. Cool. Thank you so much for talk, John. I mean, now we'll be happy to take questions from the audience in the room. Yes. Daniel Jimenez from University of Texas.
Oh,
It's Texas A&M, but
yeah, that's
I got my PhD from.
They're almost the same.
It's the same thing, yeah. No,
from Europe, it looks the same to us.
Yeah,
okay, that's fine. So I do a lot of consulting with the industry. I think the answer to the last question is there's a lot of work in academia exploring architectures that allow us to see and control it, etc. Decades of work doing that. Industry just doesn't do it because the bottom line is the bottom line. If I do this crazy thing that's going to cost a lot of design effort, how is that going to impact my bottom line? And I have to tape out in 6 months, by the way. And we're gonna, that's, I think that's the thinking, that it's incremental improvements so we can get to the next goalpost rather than,
Yeah, and I think that's what I would consider a generous interpretation. The less generous interpretation is that if you look at something like the x86 architecture, it costs on the order of $1 billion to produce a full new generation of design work, and that means that you need to recover that over your sales volume, which means your sales volume needs to be really big, and it really also helps to have nice fat profit margins. So Intel and AMD and a few other companies that still do this really have a vested interest in keeping it very expensive to enter this market. If we're in a market in which the programming model demands these humongously out of order processors in order to run software well, and it takes $1 billion to design one of those processors, well, that's good from my perspective, right? That keeps the riffraff out, lets us continue doing what we know how to do, just a little bit better every time, which is a great thing to do, and avoid nasty disruptions. But I kind of want the nasty disruptions. One of the things I didn't talk about in there is that I removed it from today's talk. 30 years ago, a computer was $1 million a processor, or $2 million a processor. And then the RISC machines came out and it was $25,000 a processor. And wow, that completely changed the market. And then in 2005, you could get about for $4,000 a processor, in a two-socket x86 system. Each of those changes completely changed the market by providing a very high volume revenue opportunity for less expensive products that then engage in a more rapid technology cycle and overtake the expensive ones. Since that last switch in about 2004, 2005, there hasn't been another switch in 20 years. And you look at people who are doing, say, oh, ARM processors, that's gonna do it. Well, heck, if you look at the price of an NVIDIA Grace, the Grace Hopper's roughly a $40,000 node for single Grace and single Hopper. So the companies know that that's where the gross margins are. And so they have very little interest in investing in alternative architectural approaches that would allow you to build inexpensive hardware that could get the job done.
Great. So your discussion about processing power, memory bandwidth, and memory latency could lead to a question about future of processing in memory, which is the question we got from Nima Samani online.
Yes, I like that. And I've looked at processing and memory approaches for the last 25 years or so. I've never felt that it was close enough for me to actually invest my career in it. But I do think from the point of view of physics, that's the way we have to go. We have to figure out how to distribute the work out closer to the memories where it's located. And that means an architecture that enables us to specify communication. Right? If you look at say the x86 architecture specification, the word communication doesn't occur. Synchronization occurs in some different contexts. They allow you to implement communication as a side effect of ordered memory references. And if you've ever worked on low-level ordered memory references, humans' brains just don't work very well that way. Human brains think in terms of causality. If I throw you a ball, you catch it, right? We understand what happened. With a memory ordering model, I have to do this thing, and then after that, I do this thing, and you're monitoring this thing, and there's several, and there are many different orders in which you could see those things happening. And if any one of those orders is incorrect, you'll find it very quickly. So yes, processing and memory, it's not just putting the processor in the memory, it's the entire ecosystem of programming languages, compilers, middleware, and not middleware for middleware's sake, right? I'm afraid sometimes people go a little overboard with software, but in order to give you the correct the correct semantic model that enables you to write programs that will effectively move things from one place to another. And once you have the architecture that specifies communication as a fundamental, then you can build hardware that treats communication differently than it treats memory references, because they're very different kinds of things. They have side effects. You want it to carry metadata, and so forth. And I think processing and memory is the way to take those architectures and make them scalable and inexpensive.
Great. To stay at the system level, we have a question about your take on the current and future role of NUMA in many core architectures.
NUMA in many core, yes, it depends. So my start in industry was in 1996. I left academia. I went to Silicon Valley. I went to work for a company called Silicon Graphics, which was just about to launch the SGI Origin 2000, which was the first really scalable NUMA shared memory system available in the market. And we absolutely loved it. And a lot of our customers loved it too. We had a box with 8 processors in it, eight cores, 4 nodes, 8 cores. You stack multiple boxes in a rack, you hook them with a cable, put racks together, put cables, and it's an SMP. You did have to pay attention to where your data was placed. First, we thought that it was going to be a latency issue for getting to the other nodes. And that is a concern. But the bigger problem was one that we didn't expect, and that was hotspots. My example that taught me about this was doing a transpose operation on a matrix. Take the rows and put them in the columns. If you write the code for that and then put an OpenMP parallelized directive, what will happen is all of the nodes will go to node 0 and say, give me my cache lines. And so you're limited by the performance of node 0, and then they will all go over to node 1, and then they'll go to node 2, and this hotspot moves around. And if you look at the average number of accesses, it's completely balanced. So why is the performance so terrible? Well, it's terrible because you've got these hotspots, and the bigger the NUMA system gets, the more serious the hotspots become. So customers were able to use up to about 32 processors, up to about 16 nodes really effectively. But once you got into especially the 128 and larger, you really, the customers didn't have the intuition for how to control the locality. And I realized later on that at the factory where I was in the design team, we knew how the hardware worked, how the compilers worked, and how the application worked. And so we could just naturally write things so that everything would fall in the right place. But the customers didn't have that advantage. And so they'd get 2 out of 3 things right and end up with a code that scaled poorly. NUMA is an important piece, but there's a risk of losing visibility into what's causing performance problems. And there's a risk of losing performance due to latency. If you try to make everything flat, you make it flat and slow. If you had programming models that you could talk about better and talk about moving data from one place to another, that might make it easier.
And the last question, now we are going to the circuit level. And the question is, what would be, in your opinion, the primary circuit level or architecture level limitation in improving memory DRAM latency?
DRAM latency. I did a write-up on this. So DRAM latency, I said, was the cycle time is 48 nanoseconds for a modern DRAM. That's if you're doing an access to a row that's already open, that corresponds to about a 12 nanosecond DRAM latency. And that's what the memory controller sees from the time it puts the read CAS request on the wires to the time the data comes back is 12 nanoseconds plus time of flight. That can't be changed because mostly can't be changed. From the sense amps, you could get it a little faster, but if you have to go to the rows, that's where you're actually reading from capacitors. And they don't want to make the capacitors any bigger because that would mean fewer bits per chip, and nobody wants that. But when you look at a system, say Sapphire Rapids with HBM, the latency, the pointer chasing latency, is about 130 nanoseconds. And of that, only 25 or so is the CAS is the activate plus CAS latency, and the rest of it is all associated with basically coherence. So on an Intel processor, there's a core sitting someplace and it misses in its L2 cache. At the edge of the L2 cache, there's a mapping unit that says this address, this physical address, belongs to one of the 60 coherence agents on the chip. And I compute the hash function to figure out which one. Then I figure out how to route the message to that unit, and the read request then goes to that unit, and it looks up the L3 at that location. It looks to see whether there are any pending transactions at that location, and it looks in the Snoop filter to see if any other cores might have a copy of that line. Then, depending on the answers to those three queries, it will maybe look up which memory controller owns the line and send it across the back and all this. And then eventually back to the core. So what ends up hurting you is the necessity to do cache coherence in cases where 99+% of your memory references are never going to conflict with anything that anybody else has ever done. But that, less than 1% is enough to give you the wrong answer. So, right. Also, you'll find software people in the kernel who say, well, but I want to have the right to move this process to another core at any time for no reason at all. And therefore, the caches must be kept coherent everywhere. So coherence is a big piece. And the size of the coherence domain is a big piece, right? So on an Intel processor, the L3 is distributed across the whole chip. In a Sapphire Rapids, that can be across 60, 4 die and 60 coherence controllers, L3 slices. Whereas on an AMD processor, a much smaller number of cores share a local private L3. And that can be accessed much more quickly, gives you much lower latency to the L3 cache. So there are always going to be some cases that give you high latency because coherence needs to be done. What you would like to be able to do architecturally is move as much as possible out of that space. If you know, for example, that you're accessing a local stack that is never going to be shared or seen by another core, there's no reason for you to do cache coherence. That comes with the additional responsibility that you have to flush the caches before, well, not before you move it, but before you restart it on the other side. And then in the communication sense, if I want to give you data, I write a cache line of data, and then I write a flag, and it bounces back and forth. And there's a minimum of 5 hops for me to convey that information to him. The way to fix that problem is to provide a message semantic so that I can say send and send it to you in 1 hop. So significant improvement. And because it's a send, it doesn't have to query anybody's caches anywhere. It's a message sent into a mailbox associated with that core.
Thanks so much. And with this, we will close the Q&A session. For the end, I have to remind you 2 things. One, we will serve coffee now. I also promised some beers on LinkedIn. This was a lie, just to get you in the room. Second, more important, John will be with us until Monday. So if you would like to talk with him, please send him an email. It's not difficult to find him online. And now I think it's important to mention people who organized this. I mean, not mention, but say thanks. Thanks a lot, because it was not trivial to make it happen. Thank you all guys for being in the room, people on Zoom, and big thanks for John for the talk today and the experience you gave us in these days at the BSc. Thank you so much.
It's a pleasure.